We know that epoxides are more reactive than typical ethers, and we can open epoxides up using acidic or basic conditions. And we're going to look at both cases. So first we're going to start with reacting an epoxide with an acid. So there's a couple of different acids that you can use. You can use the halo acids like HCl, HBr, and HI. And when you use these, H plus protonates the oxygen of the epoxide. And the halogen, X minus, acts as a nucleophile. And that's going to open up that epoxide. The other is a mixture. Maybe I should box this in just to make it clear that this is a mixture of sulfuric acid and an alcohol. And what this reagent will do is, again, the H plus protonates the oxygen. And then the alcohol, because of its lone pairs on the oxygen, acts as a nucleophile. So let's look at this example. We're going to take this epoxide and react it with HBr. So I'm going to start by actually drawing the HBr bond so that we have electrons to push. And I'm going to put the lone pairs on the oxygen. So start at the oxygen lone pair and draw a curved arrow to the proton. And then we need one more curved arrow to show those electrons leaving the proton and going on to the Br. So here we end up with a protonated epoxide plus Br minus. Now this oxygen of the epoxide being protonated is a good leaving group. And we have the option for the bromide to attack either of the epoxide carbons. It can attack here or it can attack here. Under acidic conditions, the nucleophile, whatever it might be, whether it's a halide or the alcohol, it actually attacks the more substituted carbon. And we're going to look why that is in just a moment. So if you look at the epoxide, this carbon here has 2 carbon substituents. This carbon here only has 1 carbon substituent. So the one on the left is more substituted. So under this second step, the Br minus will come in and attack this carbon and break open that epoxide. So what do we end up with? On the right, we have the OH, and there's still that methyl group. On the left, we have a new bond to the Br, and you still have the 2 methyl groups. So there's the product of this reaction. So a question you might be asking yourself is, why does the nucleophile attack the more substituted carbon? Usually for steric reasons, nucleophiles prefer to add to the less hindered side. But this is a little different because we have a protonated species. So let me draw it back out for you. And we're going to make a comparison here. So in looking at these 2 carbons, the one on the left actually has more partial positive character. And because of that, nucleophiles are attracted to positive charges, so more partial positive means more attraction to the nucleophile. Now, although what I'm going to show you here isn't part of the actual mechanism, I think it helps to make sense of this. So think about this breaking open before nucleophilic addition. We can break open on the left side, and what we get is a carbocation. Let's compare that to the other side. And if we break open on this side, let's draw what we get. We get this carbocation. Now, compare both of these carbocations. The one on the left is tertiary. The one on the right is secondary. Tertiary, we know, is more stable. And that, being the more stable source for positive charge or positive character, is why up here in the reactive intermediate, this carbon has the most delta positive character. Let's take a look at what happens when we have sulfuric acid and an alcohol. So let's predict the product and then we'll go through the mechanism. Now with this epoxide, we have two carbons of the epoxide, the one on the left and the one on the right. The one on the left is the more substituted carbon. So that's going to be the side where the nucleophile adds. And with an alcohol, what's our nucleophile? The nucleophile is the O and the R group. So in this case, OCH3. So just to draw the product, what I can do is I'm just going to start with where the epoxide was. Here's those two carbons that I've highlighted in blue. And I'll even put an extra dot on the one where the nucleophile will add, this one right here. And let's draw in the rest of the carbon chain. We have three carbons attached here. Now, when that epoxide gets opened up by the nucleophile, on the right side, we're going to end up with the OH. On the left side, we're going to have our nucleophilic group, which in this case is OCH3. All right, let's take a look at how this happens mechanistically. The first thing that happens is the epoxide reacts with H+ from the sulfuric acid. So I'll draw in those lone pairs and protonate the epoxide. Okay, from here, the conjugate base of sulfuric acid, because we just have H+ and HSO4-. HSO4- is not a nucleophile, so you don't have to worry about it adding. But what will act as a nucleophile is the methanol that's floating around. So let's involve it next. We have lone pairs on that oxygen, which that's a site of high electron density, and it can react with the epoxide. Now, a common mistake that people will sometimes make is they'll see that positive charge on the oxygen and draw their curved arrow to here. Well, even though that oxygen is positively charged, oxygen already has 3 bonds. Oxygen prefers 2 bonds. 3 is pushing it, 4 pretty much out of the question. So what do we do instead? We're going to draw our curved arrow to the more substituted carbon of the epoxide. And what that does is that breaks the carbon-oxygen bond and puts a new lone pair of electrons onto the oxygen, kind of filling that positive charge. So now we end up with the OH, and then the OCH3 group is added here. So you have the O, the CH3, and the proton at this point is still attached to the oxygen. So you have 3 bonds on the oxygen, it bears a positive charge. Now to finish this up, I'm just going to use B Anything can act as a weak base here, and just take that proton off. And here's our final product.